So FRQ number 5 is just a pulley system, and then asks us to calculate the angular acceleration of the pulley. So what I'm gonna do right now first is I'm gonna label this string right here is tx, and then this string right here is th. And I'm gonna make an equation to solve for tx and th. So we know that sigma f equals ma, right? So I'm looking at this block right here. The only force acting on this block is tx. So tx equals ma, like that. Now looking for th, there's going to be two forces acting on this block, m/2. There's going to be the force of gravity, Fg minus th equals m/2a. To isolate for th, it's going to be m/2g minus m/2a. Th is going to give you m/2g minus a, like that. Another important thing is a equals alpha r. Okay, let's get started. So part A, to find angular acceleration, we know that sigma torque equals alpha moment of arm r, and that also equals I alpha. So I'm gonna look at all the forces that are causing the torque. Tx is causing the torque, and then th is causing the torque as well, because it's on the outside of the pulley, and then it's gonna be pulling on the outside, creating making the pulley spin. And then also there's gonna be a frictional torque of 0.16 newtons times meters, which we also have to account for. So we know that th r minus tx r minus 0.16 newtons times meters. Those are all the things causing your torque, equals 1/2 m/20, which is the mass of the pulley, r squared alpha. So plugging in th, we know it's m/2 g r minus m/2 a r minus tx, which is mar, like that, minus 0.16 newtons times meters equals 1/40 mass r squared alpha. So a equals alpha r is going to be useful since we can place all these a's. So m/2 gr minus m/2 alpha r squared minus m alpha r squared minus 0.16 equals 1/40 mr squared alpha. So now I'm going to move all the ones with the terms alpha and r squared over to this side. And then also factor out the alpha and then the r squares, leaving us with m/2 plus m/40 r squared alpha. So what I'm going to do right now is I'm going to isolate for alpha. Divide this over. And then that's going to give you your alpha. So now I'm just going to plug in the values. Alpha, so 2.5, 9.8. And then when you plug that all in the calculator, you get an alpha of 30.033 rads per second squared. Next, for part B, it asks us to find the VH of the hanging block after it's ascended a distance of d, which is 2 meters. So first, I'm going to figure out A linear, which is alpha r. So plug that in. That, and that's going to give you 3.003 meters per second squared. Next, I'm going to use common form. So we know that VH final squared minus VH initial squared equals 2AD. VH initial is 0. So when you isolate for VH final, it's going to give you radical 2AD. So I'm going to plug the values in right here. 2, the acceleration we found earlier, and then 2 meters, like that. And then when you plug that in, you get a VH final of 3.466 meters per second. Part C. Part C asks us to calculate tension TH connected to the hanging mass. We found the formula for TH already. So 2.5 kilograms, 9.8, minus acceleration we found. That's going to give you a tension of 16.992 newtons. Part D. Part D is going to give us an odd situation where instead of a pulley system, it's just a rope, a uniform rope of length L and M, and then there's going to be a length Y hanging off the edge, and we have to derive an expression for the force of gravity with respect to Y. So Fg is a function of Y. So what I did was, first we need to know the mass hanging off the ledge, because that's what's causing our force of gravity. So we know that Y is a length and L is also a length. Y is part of the L. So what I did was Y over L. That's going to give me my proportion or percentage, because it's all uniform. So for like example, if the whole rope was 5 meters, and then for example at some time Y is 2 meters, that's going to give you a percentage of 40%. But since the rope is uniform, that's going to also mean that Y is also 40% of the mass. The mass of Y, length of the rope, length Y, is also going to be 40% of the mass. So right here, this is going to give you the mass of the length Y off the ledge, because Y over L gives you the proportion or percentage of the mass hanging off the ledge. So Y over L mg. G is going to be the force pulling down. So part E, derive an expression of work done by gravity on the rope as a function of Y, assuming Y is initially 0. So we know that work is force times distance, right? So we know our force is this, Fg. So Y minus L mg, and then times how much the length of the Y is, because the force of gravity is pulling down the rope a certain distance, which is Y. Y is the length of the rope hanging off the ledge. So basically what we do now is Y squared over L mg, like that. Part F, it asks us to derive an expression for the speed VR of the rope as a function of Y. So what I'm going to do now is, since we know the work, we also know work is also changing KE, which is going to be 1/2 mvr squared. There's no v initial because it's at rest, so we only need vr squared. So basically, I'm going to plug in this equation here, so it's Y squared over L mg equals 1/2 mvr squared. What I'm going to do now is I'm going to cross out the m's, and then I'm going to multiply the 2 over, so it's 2y squared g over L. Radical, it's going to give you your VR. Thank you.